I am Christopher Myburgh. I'm the Technical Director at Team Devil Games. Yeah, here's my presentation. Minimizing memory churn with examples in C#. I'd like to stop for a bit of Q&A after each slide. So some stuff that I think there's only really anything here for programmers today. So if you don't do any programming, I'm sorry I didn't have time to put pictures of lolcats and stuff for other people to enjoy, like Raxter did. But yeah, I'll try not to bore you to death. All right. Okay. Do I need to go over this? Programmers here, is anyone perhaps a bit fuzzy on what stack memory is and what heap memory is? The 30-second version. All right. Well, let's just go through the slides. Okay. All right. The stack. Okay. On the stack, objects are always destroyed in the opposite order that they are created. Very straightforward. Every thread has its own stack. Okay. Heap, things get a bit more interesting. On the heap, objects have an indeterminate lifetime. So the order that they created doesn't necessarily have any correlation with when they are destroyed. In managed environments, there's what's called a garbage collector that must periodically run to free memory from unreferenced objects, objects that are no longer in use. The heap becomes fragmented as objects are destroyed. What that basically means is if you've put a whole bunch of objects on the heap, and then in the middle of all that you go and say, well, this object can be destroyed, it's not needed anymore, you've now got a gap of unused space. And that space could be very small, in which case it's going to be very limited how it can be used again. A severely fragmented heap might cause allocations to start taking longer, which is why it's bad. All right, mark and sweep garbage collector basics. The reason I'm looking at this particular version of the garbage collector is that it's used in the implementation of Mono that's used in Unity. And also the .NET Compact framework that runs on the Xbox when you're using XNA on an Xbox console has a really simple brute force mark and sweep garbage collector. All right. So what does the garbage collector do to find the garbage? It traverses the object graph starting from static variables and the stacks for your various threads. The object graph basically means different objects will contain other objects. They'll point to further objects, and it will just start navigating this big graph, looking for stuff that's to try and find stuff that's not being used anymore. So it tags all the heap objects that it encounters, and then after that, all heap objects that remain untagged when traversal is completed are then destroyed, and the memory that they occupied can be made available again for reuse. Any questions so far?
How does stuff get put on the stack? What's the difference between the stack and the heap? Like, why are they used?
That goes into a bit more in a later slide. I compare value types and reference types. All right, but let's speak first about the major advantage of the heap, although it's more complicated, is that those objects on the heap can be accessed from anywhere else, potentially accessed from anywhere else in the runtime, whereas the stack, you can only you typically can only access a portion on top of the stack, but we'll go into a little more detail in a bit. All right, memory churn. Memory churn, this isn't actually a professional term I think I've come across before. It's just something I've kind of adopted. Maybe there's another name for it out there, in which case please let me know. But what I call memory churn is the rate of creation and destruction of objects in heap memory. All right. The higher the churn, the more severely the heap could become fragmented, the more often the garbage collector might be triggered, and the more work the garbage collector may have to do. I use like would and could and may a lot because different garbage collectors can be implemented very differently, and they can be slow in some aspects and fast in other aspects. But for the most part, if you kind of assume the worst case scenario for everything, then you're headed towards a kind of a safe spot for having your software running on a variety of different devices. Okay, a telltale sign of severe memory churn in games is small but regular pauses in the gameplay, and that's caused by the garbage collector running very frequently and taking an exceedingly long time to complete. And by exceedingly long, I mean one more entire frames. So for a frame or more, the whole game just stops while the garbage collector has to do its thing, and then it resumes. And then it stops again, and then it resumes, and it stops again. That's probably means you've got a very high rate of memory churn. All right. From the perspective of the code that you're actually writing, severe memory churn is caused by repeatedly creating heap objects with very short lifetimes. So you go and put something on the heap, you use it for a very short time, and then you forget about it, and that needs to be collected, and it has a very short lifetime, so you end up with lots of garbage that needs to be collected on a very, very regular basis. Any questions?
How does the garbage collector know when to trigger?
That will depend on the garbage collector, on how the managed runtime environment works with the memory. For instance, on the Xbox 360, using XNA, for every megabyte of data that's allocated on the heap, that will trigger the garbage collector to go and look for anything that's not used anymore. All right, next. Okay, best practices to minimize memory churn. Let's get started. All right. Okay, very simple. Avoid creating heap objects inside loops that are forgotten at the end of each iteration. Take, for example, we have, can everyone read that? A very simple type there, just a class with a method on it. And this is just kind of a pseudo C# that I'm using to demonstrate here. And, okay, that's not quite lined up, but still legible. And we have some method that's running a loop, and it needs to call another method that's on a object that's put on the heap, and you can see in this code that object is being instantiated every time the loop runs. Okay, so when this loop is done, and say for instance you've created it ran 100 times, you now all of a sudden, as soon as that loop is finished, you have 100 objects that you put on the heap that actually need to be collected again. So, simple solution for this simple scenario is just to create a single heap object before the loop and just use that over and over. Any questions? All right, next, also very straightforward, but more specific to games, is avoid creating heap objects during every update that are forgotten at the end of the update. A foo class again with a method, a hypothetical script with an update function, and you can see inside the update function, it creates an object on the heap, does something with it, and then it's just forgotten about. So every time that update method runs, you've created more garbage. You've put something else on the heap that needs to be cleaned up. That takes work and time, and it's a waste. Okay, and similar to the previous one, very simple solution is rather make that object a member of the class itself, and then just reuse it over and over inside your update. All right, any questions? Okay. All right. This one is a bit more complicated. Pool game objects that occur frequently, e.g. projectiles in a shoot 'em up. So say for instance you have a shmup, and there are all these projectiles that are flying across the screen from the player, from the enemy, over and over, and they typically only live for a few seconds at the most, as little as just a couple of frames. So if every time every every like 100 milliseconds while the player's holding down the fire button, a new projectile that gets launched from the ship has to be created. Again, there's severe memory churn that starts going on here because you're creating all these dozens of projectile objects every second that have a very short lifetime, and then all of a sudden, well, they're just garbage, and it takes time and energy to clean that up. So a solution to that is something called pooling. Okay, you see, for example, here I've declared a projectile class that can actually be disabled. And when it's disabled, then it's not currently part of the simulation at all. It's not visible, it's not interacting with anything, but the amount of memory that it needs is still reserved, is still there. And then we have, say, before I go on to that, so for example, there in Unity, projectile could be a game object, and there you already have the active self property. You can just say active self equals true or false to enable or disable it. And then we have another type here, the Projectile Manager, which actually has a little pool of these projectile objects that it keeps track of. All right, and then it has a method for providing. Okay, create projectile is a bit of a misnomer because it doesn't necessarily create a new one, but it's there to provide a projectile when one is needed. When the player presses the fire button, when an enemy ship shoots tons of projectiles. And what you can see, what's going on here is it first looks at the pool and says, is there an unused one in the pool that I can just provide and it can be reused again? If so, it just removes it from the pool. But if there isn't a spare one in the pool, then it creates a new one and makes sure it's enabled again and returns that. And then when the projectile isn't needed anymore, rather than just being forgotten and left for the garbage collector to worry about, you have something akin to a destroy method, which just disables it and goes and chucks it back into the pool for future use again. Any questions?
So if say it's a shmup and then there's a boss fight and now suddenly you're doing this full projectiles, then after the boss fight, all that memory still going to stay allocated?
Well, not necessarily. I mean, this is just the way I've written it here is just the simplest way I could think of doing it. You can get a bit more sophisticated. So maybe like a big boss. You could have one projectile manager for all the little ships in the level, and then the big boss has its own little pool, which gets destroyed when the boss is destroyed, or when the level's over, then the whole pool can just be forgotten and recollected. Or yeah, you could potentially even have one that lives throughout the scene and does all of it, or even the entire time the game is running. All right, reference types and value types in C#. If you've been programming in C# for any significant period of time, you probably know this, but I'll try and go over it quickly. Okay, first, reference types. All right, objects of reference types are always allocated on the heap. All right, and reference types in C# include any types declared with class, with interface. They include arrays, and they include delegates. Now, you can't actually create an object of an interface, but anytime you have a variable that is declared of an interface type, that is a reference, and it is referencing something on the heap. All right, okay, and just a quick note. String with a lowercase in C# is just an alias for system.string with uppercase s, which is a class. All right, value types. Okay, this is a bit more complicated. With value types, objects are allocated on the stack when declared as local variables or as method parameters, or they form part of the object on the heap when declared as class members or as the element type of an array. So if it's a member in a class, that value will actually make up part of the memory footprint for that class object that gets put on the heap. And similarly for arrays. So if you make an array of 10 values, then memory will go and be reserved for enough space to store 10 of those values on the heap. All right, value types include enums and structs. All right, structs also include your other basic numeric types, your bool, your char as well. Those are all aliases again for structs in the system namespace. Like system.int32 is what's actually being used when you just declare int. Any questions? All right. Okay. That's all pretty straightforward, and the three cases I'll show you to reduce memory churn are the first two at least are very simple, but they're not going to be useful unless they're not always going to be useful unless you're aware of the implicit heap allocations that occur in C#. So while using new followed by a delegate type or a class type or an array will always perform a heap allocation, those are far from the only places. There are other things you can do where there's syntactic sugar to hide that heap allocations are occurring. Okay, so it serves you very well to be very aware of these things. First example is string concatenation. As you can see there, some HUD text is being generated, and it's got some literals in there, name and score, and then it gets the actual values from a player object. Now, when you put a type that isn't a string inside that concatenation, the toString method is implicitly called. So, say for instance that player.score, it's an int, you call toString on there, and it's the number 3, and you call toString on there. It actually has to go to the heap and allocate a string that holds the digit 3 in it. And also when you concatenate the strings there, you don't see any new keywords, but a new string always has to be created. So I don't know if this... okay, I don't have time for that. But so just to avoid something like this, is there's system.text.string builder, which is a bit more efficient, but that's still going to require allocations. So something, if you have HUD text like this that shows the status of the player's gameplay to them, don't go and redetermine it every frame in your onRender method. Rather, save that string once somewhere and just update it every time one of these details changes. Any questions? All right, boxing. Okay. Boxing is basically when a value type is referred to as either as a reference type, in which case a copy of it has to go and be made on the heap. So the two examples that you see here are we have an int that gets assigned to another variable of an object type. So that of reference type, their object. So that number has to then go and be copied, will go and get copied onto the heap. Similarly, if you use interfaces and you have structs that implement those interfaces, and you go and refer to them by the interface type, same story. It's also part of boxing. A copy of that value will go and be placed on the heap, and the interface variable will now refer to that. Any questions? Okay, delegate creation. Alright, you can see here I have a very simple method that just tells me if a number is less than 0, and I have a whole list of these numbers, and I want to go and prune all the ones that are a list of arbitrary numbers, and I want to go and prune all the ones that are less than 0, and you'll see that first remove all over there. That's very common syntax. That's very convenient, but be aware that there's no difference between whether or not you use the new keyword and state the actual delegate type. A delegate is being created on the heap, so be careful when you use those things. You could even go and in your constructor, if you need to prune the list every frame, in your constructor you can go and create. You can have a member. Well, you can have a member in your type of predicate int, and in your constructor you can go and create that delegate reference to less than 0, and then just pass that to remove all every frame. Any questions? All right, Lambda expressions. Lambda expressions are just a special syntax for anonymous methods. And when you declare a Lambda expression, every time that code runs, it goes and creates a delegate object to reference that anonymous method. So you can see there that first removal where I say using x where x is 0, every time that runs, again, just like the previous example, an allocation is going to occur there. When you start using captured variables, that's when you use variables outside the Lambda expression that are local to the enclosing method. That's actually going to cause an additional allocation because those are captured variables are implemented as members of an anonymous class, and that class has to be instantiated. It ends up on the heap, and that's why you have 2, no matter how many captured variables you use. Any questions?
So would Lambda be slower than declaring a method?
No, not necessarily. The first example there, the delegates at the top, and the first example of the Lambda there, the only difference there at compile time is that with the delegate, we've declared a less than 0 method, whereas that method is just anonymous with the Lambda expression. So it isn't necessarily slower.
The delegate one can store it and not have to recreate it every frame.
Yeah, just like the delegate, you can go and say in your you can declare a predicate member, and in your constructor go and say assign that the following x is less than 0, just like you would a delegate, and then you can just pass that to the remove all method every frame. It gets more Lambda expressions get more expensive than delegates only when you use captured variables. Anything else? Almost done. Okay. Delegate chaining. This is not something you typically use explicitly very often, but if you have a delegate, you create a delegate and you start using pluses and plus equals, kind of like concatenating a string, every time it has to allocate a new delegate on the heap. The reason I bring this up particularly is that events by default are implemented using this delegate chaining. So every time, if there's an event and you want to register for that event or unregister from it, every time you do so, an allocation will occur. All right, for each loops, almost finished. For each loops in many but not all cases. You can see like a typical for each loop at the top there. On your MyEnumerable object, that could be an array, it could be a collection, whatever. Now, that's actually just a shorthand for what you see at the bottom there. It will look for a getEnumerator method on your enumerable object. It will call the moveNext on that enumerator in a while loop, and then it will call the current property to get the current value. When you use the for each loop in something like an update method or inside another loop, check the type of your enumerable object. Look at that getEnumerator method and look at its return type, and that'll tell you whether allocations are occurring. If the return type is a struct, then you're probably fine. If it's a class, then no, an allocation, an instance of that class has to be put on the heap. And if it's an interface, well, then either it's being implemented by a class that has to be put on the heap, or by a struct that has to be boxed, so it ends up on the heap anyway. A good example is the generic list T. If you check its getEnumerator method, it returns an object of a nested type called listTEnumerator. Now that is a struct. So if you have a variable declared of a generic list and you use the for each loop, you're fine. But if you declare that variable of the iList interface, then which returns an iEnumerator, then it's going to get boxed. And scary things like, if you look at things like string and array, their declared returned enumerators are of interface types or class types. So using for each with an array, sorry, what was the other example I just gave? yes, a string, sorry, an array or a string will actually generate garbage, at least in Mono. .NET, there's a little more hackery going on by the compiler. All right, last page. Okay, Params method arguments. The two statements, you see it's declared at the top, but can take an arbitrary number of integers, and it's very convenient to just pass all the integers as different parameters. But it's actually, those two statements are equivalent. It's actually creating an array at that point and passing that array instead. So be aware of that. Any questions?